Now we're going to get into rotational inertia. So if you enjoy this content, please like and subscribe. Before we talk about rotational inertia, let's just talk about regular inertia, the inertia we already know about, and that way we can draw a comparison. So regular inertia, we know that's the idea of mass. It's the idea of resistance. Resistance to what? Well, it's resistance to acceleration. Now, that's two different types of acceleration. That could be linear acceleration or centripetal acceleration. And we know that's the letter A. But what's this idea of rotational inertia? Well, this also has another name to it, and I'm not going to use this name very much, but you should know it because it might come up in a question, and that is moment of inertia. So moment of inertia is just another name for rotational inertia. So if inertia, regular inertia, mass, resists acceleration, what does rotational acceleration or rotational inertia resist? Well, that's resistance to angular acceleration. So the more something has of rotational inertia, the more difficult it is to angularly accelerate, or we can say to make it alpha. And this should also make sense that the more rotational inertia something has, then that means an object has a harder time changing what? Well, what does alpha do? Alpha changes angular velocity. So that would be delta W. So we know that if we have a block and we apply a net force to it, we know that that object is going to linearly accelerate. So what is going to make something alpha? What is going to make something angularly accelerate? Well, that is this idea of torque. So if we have, let's say it could be a door or something like this that has a hinge, and the door is free to pivot in these around this axis of rotation, if we apply a net force up here, and this net force is perpendicular to this R, we'll call it, radius R, then R cross F, R times F, what is that? Well, that is something called net torque. Okay, it's torque, and if it's a net force, then it's net torque. And that is a vector. Now, I don't want to get into this too deeply, but what you can think of is that a net torque will give rise to an angular acceleration. A net torque will make something alpha. Now, the real definition of this is that it will change the object's angular momentum. But again, this is more complicated, and we will get into that in a different video. And then we can draw one more comparison when we talk about net, and that would be if we have a block of mass M, and we apply a force here F1 and a smaller force here F2, then we know that the net force would be equal to F1 minus F2. So is it possible to have multiple torques? And the answer is yes. Let's say we have a radius R1 and a force that's perpendicular to that, F1, and then this force is acting on a wheel, okay? But let's say we have a different force that we'll say is F2, and that's acting at radius R2. So this torque is going to try to start to spin the wheel in a counterclockwise direction, and this torque is going to try to spin it in a clockwise direction. So our net torque in this case would be R1 cross F1 minus R2 cross F2. Now the direction of the torque is actually a cross product that is at right angles to R and F, and we will deal with the direction of net torque in a later video. So, as you would expect, there is a formula for rotational inertia, and this is the formula for a point particle. And I is rotational inertia, and this is equal to mr squared. Okay, and this is true for a point particle. And I'll give an example of this in a second. And the unit is going to be, as you could predict, a kilogram meter squared. So what does this look like? Well, let's say we have a point particle, okay, out here where the mass of this particle has a very small radius, so that we could say all of the mass is concentrated at radius r. So if we try to spin this around here, then it has a rotational inertia equal to mr squared. Well, what exactly does that mean? It means that it's resisting alpha. So if it's already spinning, what does it want to do? Well, it wants to continue to spin. And the more mass we have, the more it wants to continue in that motion. If we want to speed it up and make it start to spin faster, we need to apply a net torque. And the more mass it has, the more difficult that is to do, or also to slow it down. Now, what if we want to do this for something other than a point particle? Well, then we have to set this up as an integral. And so that's going to be I is equal to the integral of r squared dm. So we're doing this for r at all the little tiny masses that are spread out along that r. So we can actually take this formula and prove that a point particle is mr squared. So to do that, we start with I equals the integral, and we're going to do this from 0 out to r, so that would be from our axis of rotation to radius r, where this object is located, r squared dm. And we know that for a point particle that is out at radius r, that this r is constant. Well, if this r is constant, then we can pull it out of the integral sign. And we say 0 to r dm, and we just take the integral of dm, which is m, so that becomes mr squared. And we do that from 0 to r, and that's the proof that I is equal to mr squared for a point particle. Let's look at some practical examples of this idea of moment of inertia. So these are much better done in a classroom, but we're forced to imagine this because we're doing this on YouTube. So the first thing, and if your physics teacher at school has one of these apparatus, there's a thing where it's a meter stick and there's some weights out at the end of the meter stick, and on the other meter stick there's two weights that are very close together, and you can imagine trying to rotate this. So you want to spin it back and forth, and if you can picture this, the mass here's our pivot. Our mass here is further away. So when we think of mr squared, we have the same masses here as these two masses, but we have a larger radius. This is harder to start to spin, to change its angular velocity, to make it angularly accelerate. This one, you can just go back and forth very quickly. It's very easy to angularly accelerate. Another idea is ski racing. In slalom racing is where you have to go around these gates that are very close together. So you have to turn your skis very quickly. So shorter skis allow you to do that. So slalom racers use short skis because they have mr squared. They have a smaller r. And skiers that ski down a hill, which is a type called GS, giant slalom, the gates are very far apart. So you want a long, stable ski, a ski that doesn't rotate very much. So GS skis are longer. Think about someone that is tightrope walking. Why do they carry a very long bar or a long pole? And that's because a very long pole, mr squared, has a big r, so it's hard to rotate. It's hard to angularly accelerate. Here's our pivot right here. So that helps to keep the person balanced because it's not likely, or it's very hard to make it angularly accelerate. This is one you can try at home. If you have a hammer, try balancing a hammer on the bottom of the handle and try doing it from the hammer head. It's easier to do this one because here's our pivot. Most of the mass is further away. The further away that mass, the harder it's going to be to angularly accelerate. This can easily angularly accelerate because most of the mass is close to the pivot. The same idea is true here, and you can do this in your physics classroom if you have a ruler and a meter stick. The ruler is a shorter distance, a shorter r, so it's easier to angularly accelerate. You could balance this usually for minutes, and usually you can balance this for just seconds. And a final example is think about big dogs and little dogs. Big dogs walk with a very slow gait. Their legs go back and forth very slowly because mr squared. But little dogs, they just walk, they just cruise along and their feet move back and forth very quickly because they have a very small moment of inertia. What about this situation? Let's say we have a meter stick with a fixed axis of rotation at angle theta, and this one also a fixed meter stick at angle theta, same angle. And we put a mass connected to the upper part of this and a mass connected to the lower part. Who's going to win? Which one will get to the floor first? Well, this one has a lot of mass far away from this pivot, so it has a lot of moment of inertia. Therefore, it will be difficult to angularly accelerate. This one, more of the mass is concentrated near the pivot, so therefore it will be easier to angularly accelerate. So this one will win. What about pendulums? Well, if we have two pendulums that are at different lengths, and we'll say these masses are the same, then the mass here is much further away, so it has a much larger moment of inertia. So this will swing back much slower, and this will go back and forth much quicker. And this is the idea behind a grandfather clock, is the idea that the length can be set to determine the time. Now what about, this is called a physical pendulum. Let's say we hang a meter stick and a half a meter stick. Again, the same idea, more of the mass is spread out. Well, where is the concentration of mass? Well, it's at the center of mass. So we can see that the center of mass here is further from the pivot. And what about a physical pendulum versus a traditional pendulum? Well, here that R is very large, whereas here the center of mass is located here. So more of the mass is closer to the pivot. So this one will rotate back and forth more rapidly than this one. What if we want to find the moment of inertia of a bar that's rotating around its end? Now, we are going to get into other axes of rotation. For example, what if it was pivoting around here or around its center? But for now, let's start out with this one, which is what's the moment of inertia of this bar trying to spin around this axis of rotation? So we can do this sort of cheesy method to figure it out, which is to break it up into 3 chunks. And those 3 chunks, we can say the center of mass of each chunk has a certain position, L over 6, half of L, or 3L over 6, and 5L over 6, breaking this up into 6 chunks. So the idea of moment of inertia is the integral, but we can also think of integrals as summing. So let's sum all of the mr squareds. So all we're going to do is say that this chunk is 1/3 of the mass. So that would be m over 3, and we would put in L over 6 for our radius and square it. And then we do the same for the second point, and then we do the same for the third point. And when you do all of the math and work that out, you get 35/108ths ml squared. But remember, this is an approximation. That comes out to approximately 1/3 ml squared. But remember that we want to do this for all of these different points, not just approximating by the middle of 1/3 of each of these. So how do we do that? That's where we incorporate the idea of an integral. So if we say we have a bar of length L and we have its axis of rotation, what we can do is we can say R, this is 0, and this would be the maximum L, which would be our maximum R, that we can take little dm's and sum them up at all these different radii. Now, length L is the radius, and we're just going to say it's on the x-axis, so we'll call it x. So we're going to start our derivation this way. We have what we know from before, the integral of r squared dm. But we have to somehow get a dx in here so that we can integrate with regard to this little tiny position. Now, how can we do that? Well, we've done this before. We have set the idea of lambda sort of as density. In other words, it's mass per unit length. So that's m over L. So what that means is that for the entire bar divided by the entire length, that's a constant. But if we chop the bar in half, we would chop the length in half, and that ratio would maintain the same value. If we take the derivative of this, we would get dm, and we're calling our length x, so that would be dx. And we can replace dm by cross-multiplying. dm would be equal to lambda dx, and you'll see how that's going to help us here in just a second. So we can now say I is equal to the integral of x squared, and then that's going to be dm, but we know that we can sub this in for our dm. So that becomes I is equal to the integral, and we're integrating from the axis of rotation to the end of the bar. So that's going to be L. And then that's going to be x squared, subbing in, that's going to be lambda dx. Now remember that lambda is a constant, so we can pull that out. So that becomes lambda integral 0 to L x squared from integrating with respect to x dx. So now apply our integral, add 1, divide by the new exponent. So that becomes I is equal to lambda x cubed over 3 from 0 to L. So we just put in our L, and we also know that this is m over L from before. So we can say I is equal to m over L, that's our lambda, and then we put in L for x, so that becomes L cubed over 3, and one of our L's will cancel, that becomes a 2. So that is I is equal to 1/3 ml squared. So what is this? This is the moment of inertia of a bar of uniform density pivoting around its end. Now, just to sort of go into this in a little bit more detail, remember that when we did net force equations, m was the mass. We never had to do anything with that. But when we do angular acceleration, you're going to see that net torque is equal to r cross alpha, which we said, r cross f, which is also equal to I alpha. So every time we do a net torque equation, we may end up needing, if we don't know this, we may end up needing this I, but this I is different for different objects and different axes of rotation. So what is this? This is the moment of inertia for a specific situation. It's the moment of inertia of a bar spinning about its end, a fixed axis of rotation. As we said before, we just did the derivation for the moment of inertia of a bar about its end. But what if we have a bar and instead of spinning about its end, we want to spin it around its center of mass. Now, remember from the center of mass unit that if this was in space, this would naturally spin around its center of mass if we hit it or gave it a toss. When we did the moment of inertia for the bar spinning about its end, that would have to be a fixed point that would force that to be the axis of rotation. So we did I before for the bar about its end. Let's now figure out I for the bar about its center. So we're going to look at the same thing. We're going to have this bar as length L, and that little distance right there is going to be dx, and that's going to be dm. Now, we'll get into this later in the derivation, but if we choose this to be our origin, then this is going to be negative L over 2, and this is going to be positive L over 2. And the same idea that we used before is going to come up, which is mass per unit length is constant, so therefore the derivative of m, and we're going to call Lx for this, is x dx. And so cross multiplying, dm is equal to lambda dx. So let's set up our integral and start to solve it. So that's going to be r squared dm, except in this, instead of r, we're going to use x, so that becomes x squared dm. But we're going to sub in for this dm lambda dx. So that becomes I is equal to the integral of x squared lambda dx. But we know that this lambda is a constant, so this can come out. So that becomes I is equal to lambda. And what are we integrating from? Well, we're doing it from one end, negative L over 2, to the other end, positive L over 2. And that's x squared dx. So we perform our integral, add 1, divide by the new exponent. So that ends up becoming, and I'm going to do 2 steps in one here. I'm going to sub in m over L, because we know that's uniform density. And then we have x cubed over 3. And we're going to do that from negative L over 2 to positive L over 2. And that's going to give us I is equal to m over 3L, L over 2 squared, or cubed, minus m over 3L, negative L over 2 cubed. And when we do the cube of that, we end up with ml squared, because one will end up canceling the L cubed and one of the L's. And that's going to be over 24 minus, and then that's going to leave us with a minus sign. So that's going to become ml squared over 24. So what do we do when we sum those up? We end up with I equals 1/12 ml squared. What is that? That's the moment of inertia of a rod spinning about its center of mass. Now, if you think about it, we have the moment of inertia for the end, that's 1/3 ml squared. We now have it about the center, but we could drill a hole in this bar and put an axis of rotation here, or here, or here, and that there's actually an infinite amount of moments of inertia for all these different points. But we don't want to do an integration for every single time we want to find the moment of inertia. And that's where we can end up asking P.A.T. And P.A.T is the Parallel Axis Theorem, and it's a way to find the moment of inertia of any other point on an object if we know the moment of inertia about the center of mass, which now we do. Here's the Parallel Axis Theorem, which I'm just going to refer to as P.A.T in the future. P.A.T is I parallel equals I com plus md squared. Okay, what does this mean? It means the new moment of inertia that we want to find is equal to the old moment of inertia about the center of mass plus m times d squared. And d is the distance from the center of mass to the new axis of rotation. Let's look at an example of this. We could choose any single thing we want, any point along here from this center of mass. But we're going to choose the end because we've done that before. So what is d? Well, d is the distance from the original point of axis of rotation at the center of mass, and d is the distance to the new center of rotation. The new axis of rotation is better to say it that way. And as long as these two axes of rotation are parallel to each other, we can use P.A.T. Now, in this particular situation, what is this distance? What is d? Well, d would be L over 2. It's halfway. So we can say that I parallel is equal to I com plus md squared, and we know what I com is from before. I parallel is 1/12 ml squared plus md, the new distance, which is going to be L over 2 squared, and that's going to give us I parallel is equal to 1/12 ml squared plus 1/4, that's going to become 1/4 ml squared. I'm doing more steps than I need to here. So that ends up becoming I parallel equals ml squared 1/12 plus 1/4, factoring those out, and then doing the common denominator, we end up with I parallel is equal to 1/3 ml squared. Now, I've seen this question asked before, where they ask you to find the moment of inertia of a rod about its end. But they said you must do it as an integration. So although you know how to do P.A.T, and this is an easier way to do it, I would say make sure for a thin rod for this particular problem that you also know how to do the integration. For weirder things like picking here, you're probably not going to be asked to do this as an integration, and that's where you can use P.A.T.